Great, thanks, Dave. Good morning, everybody. I'm Brendan. I'm under the other fun topics section, so this is going to be a fun one. I'm going to talk about efficient exploration in deep RL via utility theory. And first, big shout out to all the collaborators that kind of try to summarize a few papers in this talk. So a big thank you to all the collaborators who have been on some of these papers. Okay, so the motivation behind this line of work was basically the observation of how the SOTA deep RL agents work in practice. So mostly they're using policy gradient style algorithms with some sort of entropy regularization, and they work really well in practice in the domains that they're tested on. And they parameterize things with deep neural networks, and they use a bunch of tricks, deep learning tricks to get performance. And I was kind of interested to see are they doing anything principled under the hood? What's going on? Why is entropy regularization so important? If you talk to some of these deep RL practitioners, they'll say things like, entropy regularization is for exploration, right? So it's not exactly correct, but it does seem to help, at least in terms of not zoning in too quickly on some fixed policy. But is there any way we can make this a bit more principled? And so basically the goal was to try to say, look, these algorithms work really well in practice. What's the closest we can come to an algorithm that actually is principled and actually satisfies some sort of regret bound or whatever, and then maybe update these algorithms in a kind of a small way to work better, and to bridge the gap between some of the tabular MDP algorithms and what is actually done in deep RL in practice. I'd say there's an absolute ton of work. I'm not the only person thinking about things like this. So tons and tons of similar people are trying to bridge the gap similarly. So that you can think of this as one approach out of many possible different ways of doing it. Okay, so since I'm mostly interested in trying to get deep RL to work better, I'm just going to consider a really simple setup. The simplest, least exotic RL framework with the finite state action, finite horizon, time inhomogeneous MDP, the usual interaction mechanism. And the only difference in the usual setup, I use L to denote the horizon. Usually people say H for the horizon. I say L because H is going to be entropy. And of course, the agent doesn't know about the environment when it starts off. It has uncertainty about the reward and the transition function, and I'm going to be Bayesian about that. So I know this is not a safe space for Bayesians. I'm taking my life in my hands here. I might get murdered after the talk, but suspend your anger about people with Bayesian, because I'm going to be Bayesian because it's a lot simpler. And also things like entropy regularization fall out more naturally from a Bayesian setting. So I'm going to have some posterior beliefs or prior beliefs. I'm just going to denote those by phi. Okay, so this is my setup, very simple. And don't expect any state-of-the-art regret bounds or anything like that, or really exotic interaction mechanisms. Is going to be very simple, and it's more about trying to get something that actually works in practice. Okay? So the agent starts off in the environment. It has all this uncertainty about the rewards and the transition function. And the question it might ask is, how does it value the uncertainty? So we know how it values the reward, but how does it value uncertainty? And in particular, if it starts off in some state here where there's no uncertainty, and far away there's some uncertainty, it needs to do two things. It needs to figure out how to value this uncertainty, so how to compress this into a number or something, and then how to propagate that back to itself. So how does it compress this into a number that I can use, and how does it translate back through the MDP? So it turns out that there's a classic way to summarize uncertainty or to value uncertainty from the economics literature called utility functions. And a utility function is just a mapping from reals to reals that encodes the risk preferences of an agent. And in our case, we're going to take the utility function to be this exponential utility function, which is parameterized by this scalar parameter tau, which is just a number. And it's just tau e to the x over tau minus 1. So that's the exponential utility function we're going to consider. And for tau positive, this is risk-seeking. This is so-called risk-seeking utility function. And the way to interpret these is via this graph here. So imagine there's this purple line here is some payoff of some lottery ticket or something, some asset, right? So you can have a positive payoff with some probability and a negative payoff with some probability. Now, if you put that through this blue line here, which is a risk-seeking exponential utility function, it's going to upweight the positives and downweight the negatives. So it's going to overall look like a positive it's going to have a positive utility. So it's like a risk-seeking agent would, prefer this outcome, even though in expectation a risk-neutral agent would understand that this has zero mean. A risk-seeking agent would have a higher utility than zero for this, right? So this is compressing the fact that there's uncertainty into like a positive number that's bigger than zero, which you can prove via Jensen's inequality that it's like optimistic for the outcome, right? And the reason we're going to pick the exponential utility is because it's the unique utility function that'll give us the Bellman equation. So in principle, you could imbue an agent with any utility function, any risk-seeking one, wouldn't even have to be convex. But it turns out for like computational reasons, you want to be able to do something like a Bellman equation to do dynamic programming, and the exponential utility function is the unique utility function that can do that. Okay. So we're going to take this exponential utility function, and it's going to convert the epistemic uncertainty into value. So it's going to, the agent starts off in this MDP with a whole bunch of uncertainty around rewards and transition functions and stuff. It doesn't know what to do. But you give it this utility function, in particular the blue line here, which is this risk-seeking epistemic utility function, and it converts everything into like some number that it can use for policy. And then in particular, it gives it this also a Bellman equation, so it can like compute everything everywhere via dynamic programming and get a single value that combines the reward and the uncertainty into one. And I'm using J to represent that value because there's still also the V value of the true MDP with the rewards. So I'm distinguishing between V and J to say one is the risk-seeking value, which is going to be bigger than the expected value of the true value function, which is V. Okay, so this is like the setup. We've given the agent an epistemic utility function, or risk-seeking utility function, exponential, and it's going to like compute these value functions. Okay, so how do you get these value functions? Well, in the utility literature, there's this thing called the certainty equivalent value under utility, which is the value of a certain payoff of equal value to the uncertain payoff. So the uncertain payoff is this like random variable x, let's say. You pass that through your utility function. You take the expected value, so you integrate out x, and then you inverse the utility function, and that gives you the kind of the equivalent value you would take of a certain payoff that has the uncertain payoff. So it's summarizing a random variable through your utility function and getting back to a utility value. So this is that, and this is like if this has units of dollars, then this would have units of dollars, and this is like a classic thing in the utility literature. Okay, so with the exponential risk-seeking utility function, if you just do this with the u I provided earlier, you get this value, which is like tau log expect exp, right? And this part here is, we recognize it as the cumulant generating function of the random variable x, or the log of the moment generating function. And like everywhere else, I'm going to assume in a bunch of places that things are sub-Gaussian. So with the sub-Gaussian random variable, like the definition is that this cumulant generating function satisfies this kind of inequality, and in particular that specifies that the utility is also bounded by an inequality. And this utility then is saying, look, if you make this an equals, let's say if it's Gaussian, it's saying the utility is equal to like the average reward you would expect to get, or the average outcome, plus something that depends on the uncertainty. This is like the epistemic uncertainty, and this tau parameter is kind of what's blending the two together. It's risk-seeking, so tau is positive, so it's going to like give you a bonus or an optimism bonus for the utility function. Okay, so that's our utility values, and in reinforcement learning, dynamic programming, it's not just about computing a bunch of utilities. We want to be make a decision that's maximizing some value function, whatever it might be. So we're going to have to convert these max over a collection of random variables into this utility language. And we're just going to use some standard techniques to do that. So for a collection of random variables, xi, you can just upper bound the expected value of the max using this standard trick from like extreme value theory or whatever, where you basically just put a log and an exp here, you move the max out, and then you replace the max with the sum, and you get this quantity here, which is true for any tau positive. But now we have this like expected value of this xi. We're going to replace that with the utility, because that's what this is the log of the utility, so we just replace the utility. And now we have this tau log sum exp. Now this is starting to look like these soft Bellman equations, right, that we see in a bunch of places. And the next step is then to say, or the next idea is to say, well, log sum exp and entropy are convex conjugates of one another, which means that you can rewrite this log sum exp term as like a max over what turns out to be policies. So I'm just going to say it's a policy. So a max over policies of this linear term, so the expected utility plus tau times the entropy of that policy. And this is just a result in convex analysis that relates this log sum x term and entropy. They're convex conjugates of each other. And the policy that achieves this maximum is just proportional to these utility values. Okay? So we've gone from this expected value of the max of a bunch of random variables, which is like a complicated and annoying thing to deal with, but we were able to upper bound it by something that takes in the utility functions and computes a policy, and then like you can use that policy as later we'll see you can use that policy. Okay, so we're getting close to something that looks like an algorithm and a regret bound. So like let's, as a warm-up, just do it in a super simple multi-arm bandit case. So now the MDP, or the problem is just a tuple of the actions and the rewards. And again, I'm going to assume this is a bit hand-wavy, but I'm going to assume a sub-Gaussian posterior over arm rewards. You can make that more concrete. And here's the algorithm. I'm just going to, for every time period, for every arm, this is the simplest stochastic multi-arm bandit case. I'm going to compute these utility values based on these equations back here. This cumulative generating function thing for a particular choice of tau, which is going to let's say satisfy some schedule or something like that. So I'm going to compute all the utility values. Then I'm going to compute this policy. So it's a stochastic policy, stationary stochastic policy. That's just going to be like the Boltzmann or Gibbs policy of those utilities with this temperature tau. And now I'm going to run that. And so let's see what the Bayesian regret. So again, and a lot of people are angry when they see Bayesian regret, but let's just, for the sake of argument, just run with it. So the Bayesian regret is just the expectation under the prior of the regular regret. And so we have this expected max. I'm going to replace that with what I just had on the previous slide, which is like in the previous slide here, I had the expected value of a max, and I was able to upper bound that by this quantity here, which just depends on the average utility plus the entropy. And like this max here, as long as I use this policy, which is what I'm using, then I can just plug in that pi. So that's what I'm going to do, plug in that pi. Whoops. So I get the average utility plus tau times the entropy minus my expected reward based on what I'm pulling the policy. Then the sub-Gaussian, this utility is, I'm assuming, is sub-Gaussian, so I just upper bound that with the normal sub-Gaussian quantities, which are to replace it with the mean plus something that depends on the epistemic uncertainty of each arm. And then notice these two terms cancel, and all I'm left with is two terms, one of which is something like the uncertainty of each arm, which should go down with data. As you collect more data, this goes to 0. And another thing that's bounded by log A, because it's the entropy, and this is like a finite arm stochastic multi-arm bandit. And I have two taus, one, in the usual case in like online learning, I've got one that's, 1 over tau plus something that depends on tau. So I'm going to just, as long as I can assume that again, it's a bit hand-wavy, but assume that this uncertainty goes down like 1 over the number of pulls. You can make that rigorous. So it's like something like Gaussian, let's say. So the amount of times I pull each arm, my uncertainty should concentrate like 1 over that number of counts. Then I can just look at this and just use a pigeonhole principle to be able to bound that and then optimize over these choice of temperatures to get this like final Bayesian regret bound. So this is not like shaving off any constants or anything like that. This just matches other Bayesian regret bounds. We're not trying to get state of the art here, but we're building the intuition that this utility function approach, where we're able to compute utility values for uncertainty, then run a Boltzmann policy with that temperature over those utility values is actually able to work in practice. Okay, so that was the warm-up, which is just multi-arm bandits, but we actually care about RL. So again, we're going to, in the RL case, there's the two unknowns, is the reward function and the transition function, which are captured in our beliefs, our posterior beliefs phi. I'm going to go again with a warm-up and do an even simpler case where these are known, these p's are known. We'll come back to it and fix that later, but this is just the super, super simple, an MDP with just only unknown rewards. And in that case, you can just go through the exact same thing we did for the bandits. You can say your random variables are Q stars, you compute like some utility function, certainty equivalent value of the utility function, which depends on these U's, which will introduce the temperatures. Then this certainty equivalent value satisfies a Bellman recursion. So you can basically roll this out by just expanding the definition of Q star inside the exp, and you get this like Bellman recursion for this like risk-seeking Bellman operator, which I'll say on the next slide. So you have but this is a Bellman inequality. But now we just say, okay, I'm going to just define K, which I had before as the exact utility, and I'm just going to have K as the fixed point of this Bellman equation. And due to the monotonicity of the Bellman operator, it's an upper bound on the true utility function. So now I'm just saying these K values are upper bounds on the risk-seeking certainty equivalent values under that utility function with that temperature tau. So then, putting that all together, what does the algorithm look like, or what do the equations look like? You solve some Bellman equation that has the mean reward plus some bonus that depends on the uncertainty. If we make a sub-Gaussian assumption on the rewards again, so you have some mean reward plus some bonus that depends on the uncertainty where the temperature appears here, plus the value at the next step, and the value in this case is like this softmax thing, this log sum x, which is related to the policy here by this maximum, by this convex conjugate relationship between log sum x and entropy. And again, this policy is just like the exponential, the Gibbs or the Boltzmann over these K values. So that's the whole algorithm. You solve these Bellman equations, and then you run this policy, and then you will see that you get the same regret bound. In fact, the regret analysis is essentially identical to the multi-arm bandit approach, where we just like upper bound the expected value of the maxes. The only difference is instead of getting one term of uncertainty, you just have to telescope out the terms to get a bunch of sum of uncertainties, but it's the same idea. Then if you just assume that the reward uncertainties, these epistemic uncertainties, also concentrate like 1 over the visitation counts, then you can just do what we did before for the multi-arm bandit. You first telescope this sum, you get a bunch of these, a bunch of uncertainties, then you use the pigeonhole principle again and optimize over temperature again, and you get this Bayesian regret bound of root SAT. Now you might be wondering, where's the horizon? It's because we're in the really simplified setting of like known P. Because of the known P, doesn't depend on the horizon yet, but it will in a second. Okay, so that's the approach, is to compute these utility values, solve a Bellman equation that brings all the uncertainty into one number and propagates it through the MDP into these K values, which are capturing the certainty equivalent utility under this exponential risk-seeking utility function, and then run the policy associated with that, this Gibbs or Boltzmann policy with that temperature. The only wrinkle is like, how do you choose the temperature? And there's two ways to do it. You can via this analysis, where you do this telescoping and you optimize explicitly over the temperature, you can come up with a schedule. Or you can actually solve a convex optimization problem that's joint in tau and these K values, where now these K values like satisfy a Bellman inequality, and that will give you like the optimal, in some sense, temperatures to run. And actually, in practice, this is much better. They get the same regret bound, but this one does much better. The same regret, Bayesian regret upper bound, but the Bayesian regret of this one is bounded above by this one, so this one is better. And also, we'll come to later how we explicitly optimize this in an online setting for this deep RL that we care about. So this is the approach we should be taking, which is to solve the convex optimization problem jointly in tau and K. And this is like a generalization of the linear programming approach to dynamic programming, where now we've, rather than just being risk neutral, we've like given the agent some risk-seeking utility function, and that changes the convex optimization problem to get the value functions. But it's basically the same idea. Okay, so that's how we're going to do it. Now, the last thing is, of course, is to fix the problem we have, which is that we were in a known P case. That turns out to be relatively straightforward, based on a result that Ian Osman and Ben Van Rooij put out a few years ago, which is called the Dirichlet-Gaussian posterior dominance, which is, okay, if you have the original posterior over your rewards and your transition function, and now I'm going to make two additional assumptions that are required by this result, which is that the rewards are bounded, say between 0 and 1, and we have a Dirichlet prior on P. So it's a little bit more restrictive than the previous setting. So there's a couple of extra assumptions. So you have some original posterior that's including uncertainty in both the rewards and the transition function. It turns out you can transform that posterior where you replace the uncertainty in P with just its mean. So you replace the posterior over P with just its mean value, and you shove a bunch of extra uncertainty into the rewards. So you've transformed it from unknown R, unknown P to known P, but much less known R. So like inflating the posterior over R. You can run an algorithm in that case. So you can run an algorithm for the known transition function on that transformed posterior, where the uncertainty in P has been shoved into the rewards. That'll get some regret bound, in the known R case. What you care about is the regret bound in the original case. It turns out it just inflates the regret bound by a factor of L. So it's like a generic for any algorithm that can work and get a Bayesian regret. Again, like save your anger for the Bayesian regret stuff. For any algorithm that works in the Bayesian case, if you get Bayesian regret for the known P case, you can just do this procedure where you move the uncertainty from P into R, run this algorithm iteratively on the known P case with this extra uncertainty in R. Whatever Bayesian regret you would get in the known P case, you just multiply that by like a constant that depends on L, and that'll give you a Bayesian regret implication for the original posterior. Yep. Yep. It's because basically this paper from Ian and Ben, it basically implies a posterior dominance, like a second order stochastic dominance result of a Gaussian distribution over a Dirichlet distribution. So you have to have the Dirichlet distribution in order to get. And because we have that stochastic dominance result, it basically the value function upper bounds the other value function, and then we can compute the regret. So it has to be Dirichlet. So that is a bit of a restriction, but it's not too much of a restriction, I think. Okay, so that's how we get the final regret bound for this algorithm. Again, it's not state of the art or anything like that. I think it's off by a factor of root L from the best one. So it's an L root SAT regret bound for this utility approach. And this actually ends up matching kind of the Thompson sampling regret bounds in this very simple tabular finite horizon case. Yeah, sorry. Yeah. 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 Yeah, you update every episode. You update. So you basically you have uncertainty in RMP for every episode. You replace P with its mean, and you add a bunch of uncertainty to R. Then you run that algorithm that can work with a known P, and then you get a bunch of new data. You use that to update the posterior for P again, and you got a new mean, and then you run that again. Yeah, it's a bit confusing on the slide here, but yeah. Okay, so the summary so far is imbued an agent with this exponential epistemic rich-seeking utility function that allowed us to come up with a bunch of Bellman equations that were kind of like these soft Bellman equations that we see in what people do in deep RL, like soft actor critic and soft Q learning. People run those a lot, and they're quite effective. Also, entropy regularization fell out of it. Optimism, obviously, from the risk-seeking utility function, and this like Boltzmann or Gibbs exploration policy with the temperature. And then we were able to actually say that these satisfied a Bayesian regret bound. So we could actually run this in a tabular setting and get this like not state-of-the-art Bayesian regret bound. Okay, how does this relate to practical deep RL? So that was just kind of the trying to get what people do in practice onto some kind of like principled grounding. And now we want to actually figure out a way to take the algorithms that people run in practice and modify them a little bit to be closer to this. Now, I don't have a Bayesian regret bound for or any type of regret bound for like the rest of these results, but it's more about like trying to get these algorithms to be a little bit closer to something that actually works in practice. So people do a lot of policy gradient, entropy regularized policy gradient, so we're going to do entropy regularized policy gradient instead of trying to solve all the Bellman equations, which is like a model-based approach, trying to be online model-free, and do it in terms of the policy rather than in terms of the action values. So in the Bellman equations in terms of a policy for this epistemic risk-seeking value function are very similar, except instead of this log sum x, the softmax, you just have whatever your policy is, like your expected value of the action values, but you also pick up an entropy regularizer, also kind of appears, and you still have this bonus in the epistemic uncertainty. Okay, so what we're going to do is try to maximize over this policy, maximize these values over the policy. So we want to solve a saddle point problem where we're maximizing this policy, but we're also, like I was saying before, we're going to minimize over the temperature based on basically the intuition from like all the way back here, where we could, jointly minimize over tau and k to, pick the best temperature, which does a lot better than the schedule. So we're going to maximize over policy and minimize over temperature. So this saddle point objective. And if you were able to do this, you would just get, if you did this exactly, you'll just recover the exact, Boltzmann policy that if you'd solved the Bellman equation exactly and so on. So the policy player is trying to find like an optimistic policy that maximizes the value function. And the temperature tau player is trying to like tune the temperature, the optimism to minimize, we'll see in a second what it's doing. Okay, so it turns out you can prove a result that says for any policy, the per episode Bayesian regret can be decomposed into two terms, or upper bounded by a decomposition into two terms for any choice of tau, one of which is a kind of a distance measure. It's the KL divergence, or like the expected KL divergence from your current policy to what the optimal optimistic policy is. It's like Gibbs thing. So there's like one term is like the distance you are from the best policy you could be, and then the other term is like how much does J pi overestimate V pi, like the expected value of V pi. So you can, for any policy, you can upper bound the Bayesian regret by the sum of these two terms. And it turns out that finding the saddle point of this value function, this Lagrangian or whatever, is equivalent to minimizing these two components individually. So there's a result in one of these papers where we show that the per episode Bayesian regret, if you find the minimax point over pi and tau of this value function, assuming that strong duality attains, so it's a bit of a restriction, that you are basically minimizing individually these two components. So you're basically, if this term might go to zero if you're able to exactly represent the policy, but if you're in a function approximation case, you might not actually be able to exactly represent the policy. So you pick up a term that depends on like how well you're able to approximate the policy, plus like your minimum of your optimism, this is your usual source of regret. This is what we were able to bound with root t, but now there's like an additional term, which is like how far away you are from the true optimal, or not true optimal, but the optimal optimistic policy, following all this like this epistemic risk-seeking stuff. Yeah. Here? Yeah, so I think it's because, why did it? Yeah, I think pi, so little pi asterisk, tau asterisk are the solutions to this problem. So the L here should be J, right? So the J is, so replace L with J in your brains. And this max over, this might be a restricted set. So you'll get a pi asterisk, tau asterisk that are not necessarily pi star, tau star, which are the unrestricted versions. So this is like the distance between pi and the true pi star, and this should be a tau star here, actually. Is that what you're asking? This should be a tau star. And this is tau asterisk, because it's what you actually, this one is tau asterisk. Well, it's because like this pi, why does it depend on tau asterisk? I think it's because I think the KL penalties, or this distance is really a KL. I think they're weighted by tau, whatever the tau is. Yeah. So that's just like fixed by that's the best thing you can do right now under the posterior. Now you're in a different setting where you have like a function approximation. And you want to get as close as you can to that. So that's like some pi star, tau star, they're the best. You're in a function approximation setting, you solve your saddle point problem in this other setting, you get a different pi asterisk, tau asterisk, which is different. And then they plug in here in this way. No. No, yeah. Well, no, yeah, that's a good. So if you actually did, so you could imagine, like, let's go back to this one. Why not just like minimize this entire sum over both pi and tau? It turns out that gets linear regret, because you're basically too greedy. You end up being like, oh, I can like minimize my Bayesian regret in this one episode. I can make it as small as possible in this one episode. Then you don't learn anything. You don't like explore enough. It turns out the right thing to do, which is weird, is to minimize the two components individually. And you get that automatically by solving this saddle point problem. So it's a bit odd, but that's how it falls out. Okay, so yeah, so the solving this saddle point problem, or maximizing the value function, is attempting to solve this problem where the two components of the Bayesian regret upper bounds are minimized. So it turns out that this entropy regularized policy gradients that people do in practice are kind of trying to minimize the Bayesian regret, kind of. They're missing a few components, but they're getting close. And so if we look specifically at the gradients, let's say we parameterize our policy by some theta, then, and tau is just a scalar, so we just take the gradient with respect to that scalar, then the two gradients, or the gradient with respect to theta is just trying to minimize the approximation error. So this is like a gradient of the distance, and the gradient with respect to the optimism with tau is just trying to reduce the overestimation, which they're both trying to push down the Bayesian regret. So it looks like they're maxi-min, they're against each other when they're the two players are competing when they're trying to solve this problem. Actually, it turns out that they're kind of working together to try to minimize their Bayesian regret upper bound. Okay, so I'm just going to do that. That's what I'm going to actually run as an algorithm, which is this simultaneous gradient descent ascent. So I'm going to do standard entropy regularized policy gradient over these parameters of the policy, which are now a neural network or something. And the only difference to regular policy gradient is that this critic is the risk-seeking action value rather than just like the value. And I have like entropy regularization here, which comes out naturally, and is what's done in practice. And now I have an additional term, an additional gradient for the taus, which are the temperature parameters. In deep RL, usually that's just fixed hyperparameter, but in practice, you can actually learn it via this this gradient procedure. And I'm just going to run the two together. So I'm just going to do a gradient ascent on the theta and gradient descent on the taus simultaneously. There are much more sophisticated things you can do, but yeah. No. So it's still the derivative of j with respect to both terms, but it just turns out that you can decompose the Bayesian regret into these two terms, and when you take the minimum of j, or the maxi-min of this value function, it's equivalent to minimizing the two terms in separately. But you might ask, as Gergo did, why not just minimize the entire thing? Is that better? And it turns out that's too greedy, and you don't explore enough, and that gets linear regret. And what you actually want to do is what is happening naturally, which is to minimize the two components individually. Okay, so I'm going to run this algorithm, this simultaneous gradient ascent descent, and here it is in like an algorithm box that's basically a copy and paste of a deep RL algorithm box, where I've just modified it with these blue terms. So anything in blue is a modification of like a standard actor critic to incorporate this additional, epistemic risk-seeking stuff. So it's called epistemic risk-seeking actor critic. So the only differences are, first of all, you learn the taus rather than just have it fixed temperature parameter. So like typically in the deep RL, you have entropy regularization as just a fixed hyperparameter. So the first difference is that you actually try to learn it on the fly. And the second differences are that you have the second big difference is that you have these additional uncertainties that you need to compute. So these need to come from somewhere. And then once you have those two things, you can just plug it all together. And now you have like a relatively small change from what is like basically what's done in practice in deep RL, these actor critics with like a bunch of tricks. But this is basically the high-level algorithm. With a very small change, we're getting close to something that actually has like a Bayesian regret band. Okay, so the only thing is like I mentioned is that we need some source of uncertainty. So in the experiments I'm going to show you, the source of uncertainty is, so the sigma is going to be just the standard deviation of a bunch of an ensemble of reward predictors. It could be anything, there's lots of different ways to estimate uncertainty in deep RL, But just for this simple experiments, I just try to learn the reward at every state in action, and I learn it in such a way that there's like some standard, there's some difference between them, and then that standard deviation should go to 0. So that's the only network architecture change I need to make to this thing. Okay, so everyone's favorite environment to try the exploration algorithms on is this thing called deep sea, where there's a diver who starts off in the top left here in a boat, and he is going to swim down to the bottom, and there's some gold somewhere at the bottom that he has to find, and it turns out he has to make the exact right sequence of actions to get to the gold. So he has to go right, and if he ever makes a left, he can't get to the gold. So he has to explore. It's a hard exploration problem because if he ever makes even one mistake, one deviation from the optimal path, he doesn't get the gold. So it's a quite hard exploration problem. So like if you imagine just doing random dithering, a 50-50, that it would take you like exponential in the depth to get to the gold, because you have to get the exact right sequence of actions. So this is a hard exploration problem. We also give a little penalty, a little negative reward for taking the right action, so that to disincentivize the right action, which is overwhelmed by the total reward if you do get to the bottom. And we're going to run this so this is a tabular environment that is set up here, but we're not going to run it tabular. It's going to be a real deep RL setup where we pass this in as an observation to a normal neural network and a couple of layers of neural network, and then get it to produce the policy. So even though it looks like a tabular, we're not going to run tabular. These are real neural network deep RL experiments. And the one additional factor you have to do when it comes to deep RL is you can't have always be right be the optimal action, because what will happen is randomly the agent will have like a slight bias in one episode for right, and then it'll just sample right by accident, and it'll get to the gold. So what you need to do is for every state in action, for every state rather, if the agent is producing action 0 and 1, you just change which one corresponds to left and right depending on the action. So it's not, rather than being right, it's really more of a sequence of like 0, 1, 1, 1, 0, some sequence of bits that it has to get right, just to prevent like random accidental biases which don't affect tabular agents solving the problem too easily. So this is genuinely a hard exploration problem. Okay, so as a baseline, I'm going to take Muesli, which is it's a couple of years old now, but at the time was basically a state-of-the-art policy optimization algorithm which combined all the tricks in deep RL into one policy optimization algorithm. So it does like a whole bunch of replay. It does, I think it's an actor critic under the hood, but it does kind of this model-based stuff. It does these like important sampling replay things. And anyway, it was at the time like basically state-of-the-art for a bunch of environments. So the question is, how does Muesli do, this very heavyweight algorithm with multiple actors and all sorts of stuff, do on deep sea? So it does terribly is the answer. So here on the x-axis is like the depth of the deep sea. So every point here is a new environment of a different depth. On the y-axis is how many episodes until Muesli was able to solve that depth of problem reliably. And with these red dots up here, it means it didn't solve it within 100,000 episodes. And this gray dashed line is is exponential. So it's like if you were a random agent, you'd expect to have a curve that looked like this. So Muesli is not able to solve even the most shallow of these deep seas, like depth 10 or whatever this is, which you would expect to get in about 2 to the 10 episodes, like 1,000 episodes. It can't do it. And I think the reason is that Muesli, like a lot of other state-of-the-art RL algorithms, are extremely greedy with the observations they've already seen, and because of the negative reward that the agent gets when it takes the right action, it pretty quickly learns not to take that action, and then it just locks in on that. Oh, okay, run out of time here. Okay, so then let's compare some. That was a state-of-the-art deep RL agent, but let's be a bit more, little less state-of-the-art. So how does vanilla actor critic do? So basically this algorithm, but without the blue stuff, so normal actor critic, it basically follows the exponential line. It has no principled way of doing exploration. Entropy alone is not enough entropy regularization, and it basically follows the gray dashed exponential line and fails at 100,000 episodes. What if you just add a bonus? You just do exactly the same thing, entropy regularized actor critic, but you just add a fixed bonus. How does that do? Well, that does actually a lot better, but still kind of breaks down at some point. Another algorithm is bootstrap DQN, which is kind of like neural network-based approximation to Thompson sampling, and that does a lot better, but it kind of fails catastrophically at some point. I think, I'm not sure entirely why that happens. And I did experiment a lot with this, and I was able to maybe get it out to 50 or 60, depending on the settings that were different from different agents, but it kind of does eventually break down catastrophically. It's Ensemble Plus. Yeah, with the randomized priors. Yeah, with the randomized priors. Yeah, yeah. I think it's just I think if you had more and more and more particles, it does better. But even when I add like hundreds or thousands of ensemble members, it did still eventually start to break down like 50 or 60. Yeah. Yeah, sure. I can talk about it offline. I've got lots of experiments to try to get bootstrap DQN to work better on it. And then, so the epistemic risk-seeking actor critic, which is just this algorithm back here with the blue included, this basically scales gracefully out to much higher depths than typically we run BSP for, like out to 100, and it has this like quadratic dependence. So here's some videos of just what's actually happening. So again, this is a tabular environment, but we're running it in like with real deep RL. So here's a vanilla actor critic, and you can see this is like basically the grid of the environment. And each blue line here is a real trajectory that the agent takes. And the gold, the reward is down here. And it can kind of, from the dithering and the entry regularization, it does kind of get a little bit into towards the reward, but doesn't really get much past like 10 or 20. And it mostly focuses around the start, and it just isn't really able to ever make any progress. And that's why we see like these exponential dependence on depth. Whereas the epistemic risk-seeking actor critic, again, this is all deep RL, but it's able to, gradually just move over towards and mine away, pick up the reward that it gets from uncertainty because of this exponential epistemic risk-seeking utility function. It gets a reward for going to uncertain states, and it brings it back, and eventually it finds the reward and it locks on. It does a few little random explorations and other things, but it gradually locks on and is able to repeatedly go back there. Okay, so there's like qualitative difference there in the behavior between just a relatively minor addition to vanilla actor critic. It's like 2 or 3 extra lines of the algorithm, and made a big difference to the actual performance. Okay, and so I don't have a regret bound for the online version, but it seems to empirically get something like a depth squared dependence in terms of this regret. So it seems to be, I'm hopeful that there is a possibility of being able to solve or prove a regret bound for the online case. I just mean these gradients, like applying these gradients. Yeah. And then so one bit of feedback I got when I was working on this was that even if it did work, it would never be able to use replay, and so it would never actually be able to like be a state-of-the-art policy gradient agent. But it turns out you can. So all these tricks that like Muesli do, they all use tons of replay, which is actually very important for policy gradient performance. So just the pure online, so no replay version, is these blue dots. But if you add replay data, you make sure you add tricks to prevent the uncertainty collapsing, you can actually improve performance. So it still works, and in fact, it does a lot better. This is out to like depth 150, so it's like really, this is like a random agent would take like much longer than the age of the universe to solve this problem or something like that. Okay, I'm basically done. I think that's the end. Yeah, of course, Atari results, it does better. Yeah. Conclusions. So we started off by just imbuing an agent with this exponential epistemic risk-seeking utility function that allowed us to derive these like soft Bellman equations, the entropy regularization, the optimism fell out naturally in these Boltzmann policies. The dual view gave this like 2-player zero-sum game between the policy and the temperature. When they do a policy gradient and simultaneously learn the temperature, where it turns out that each player is actually minimizing a separate component of this like Bayesian regret decomposition. So even a policy gradient, which I'm trying to get as close as we can to these like deep RL algorithms, they are doing something with respect to a Bayesian regret. It works with deep learning. In practice, like it's a relatively small change to what actually happens for deep RL. I skipped some. There are some deep connections to Thompson sampling. You can prove some like pretty interesting connections to Thompson sampling. But the difference is that Thompson sampling is like a sampling-based approach. This is like an optimization-based approach because we're solving an optimization problem. Because of that, Thompson sampling ends up having linear regret and constrained MDPs in 2-player games, whereas the optimization problem, you can incorporate constraints in 2-player games a bit easier. Also, I skipped that you can in this case, in the setup we had, there was like one temperature for the entire MDP. That that doesn't really make sense. You should have like different risk-seeking parameters based on how certain you are about different regions of the space. And it turns out you can actually totally break apart this, instead of having one temperature, have a totally state action dependent temperature instead of a single one. And like I was mentioning, it would be great to get a regret bound for this like online policy gradient version of the algorithm. Cool, that's everything. Thanks very much. Any questions? Yeah. Why it's not what? Oh, well, it turns out it is. But I think the intuition that people had was that if you tried to do replay for policy gradients, you'd end up like, maybe killing the uncertainty or something like that. Your uncertainty bonus would go to 0 or something. And then you wouldn't explore enough because replay, if you have something that's estimating the uncertainty, if you push a bunch of replay through that uncertainty will probably go to 0, right? Like the ensemble of reward predictors would eventually start to agree if you do enough replay. But so if you just do a couple of tricks to prevent that happening, that goes away. Yeah. 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 I'm not entirely sure why they're different, like the performance. Yeah. That means just take the exact same way of producing the uncertainty as with the ensemble, and just add a bonus, which is like sigma rather than sigma squared times some lambda, some fixed hyperparameter, and just add it as a bonus everywhere. And then also fix the temperature parameter, which is like the entropy regularizer. So there's two differences there. So it seems that the temperature parameter that we're learning balances the entropy and the bonus that arises from the uncertainty. So it appears in both places, and the gradient is like incorporates the gradient of with respect to the temperature, has both terms. Right? It has the uncertainty and the entropy. Actually, I think that might be the wrong. Oh no, that's correct there. Yeah, and so somehow learning that temperature seems to do a little bit better than just fixing a bonus. Well, so the temperature is being tuned on it like automatically, and it's balancing. It's tuning. It's like weighting the entropy. Yeah. Yeah, I think a big part of the benefit is coming from picking the right tau, which it learns on the fly rather than just having a fixed hyperparameter.